Welcome everybody to the online seminar series Machine Learning Needs Mathematical Optimization. So we are very pleased to have today Paula Brito. She's an associate professor in statistics and data analysis at the Faculty of Economics of the University of Porto, and she's also a member of the Laboratory in Artificial Intelligence and Decision Support at the same university. So Paula did her PhD in France at the University of Paris 9, and she was also in a postdoctoral position abroad, and then she returned to Portugal. She has expertise in on clustering and analysis of symbolic data. And her work has appeared in renowned journals in the field of statistics and operations research, such as European Journal of Operational Research and Advances in Data Analysis and Classification. She has ample editorial service, including journals such as Computational Statistics and Data Analysis. And she has also an ample record of service to the community, and for instance, she has been the president of the International Association for Statistical Computing. So we are very pleased to have today Paula talking to us about discriminant analysis of distributional data. So for the audience, you probably know how we organize things here. So if you have very, very urgent questions, please raise your hand, and we will read the question from Paula, and otherwise we postpone all the questions towards the end of the seminar. Thank you so much, everybody, and the floor is yours, Paula.
Thank you very much, Dolores. And of course, I would like to start by thanking the organizers, Dolores, Emilio, and Cristina, and other colleagues for inviting me for giving a seminar in your series. And of course, congratulate you on this initiative and this organization. This is really a big success. I've attended quite a few, not all, but quite a few, always interesting topics, great speakers, and very, very successful organization. So congratulations and thank you. And I should start by a disclaimer, as it perhaps was made clear by Dolores' introduction. I am not an optimizer. I've never worked in optimization. My background is in fact statistics, and more specifically multivariate data analysis. I used to say that I'm a product of the French school of analyse des données and its tradition. But my thesis supervisor, long ago, Professor Diday in France, was himself started in optimization and operations research. So the things are connected, and it's clear that in data analysis, we do need optimization every pass of the way. So now, starting. I know that the title of the talk is somehow a bit provocative. But whether or not you are indeed bored by the usual classical data, the so-called simple numbers, I hope that with the talk can make clear that there's something beyond the simple numbers, that are new perspectives in data analysis, and there's a field of development to be made, posing new challenges for us all. If I'm successful at the end, perhaps you'll get new ideas. This work, today I'm focusing on discriminant analysis for distributional data, and we'll soon see what I mean by this. And this is joint work with Sonia Dias from the Polytechnic Institute of Viana do Castelo and Paula Amaral from Nova University of Lisbon. So, sorry, here. This is the outline, so I'll start by some brief motivation for this approach and how it's done by the need to take into account variability in the data. And this led to the development and is now done in the framework of the field of symbolic data analysis. Then we concentrate on a specific application, which is a bacterial classification problem, where the data does include variability. So once presented the problem, we'll see how we model distributional data, what are the properties, and how we take this variability into account. We then proceed to the specific methodology of discriminant analysis, see how we define the linear discriminant function in the for distributional data, and how we proceed to classification in the case of two groups. We present also some short results of a simulation study that allows understanding how the method behaves. Then back to our biological classification, we see how the method allowed to classify the bacteria species in between the two groups of gram-positive versus gram-negative. And then I finish by drawing some conclusions and pointing out perspectives for further research. So, starting. So, distributional data. You must have started by asking yourself, what does she mean by this? Data that are distributions, what is this? So in what we now call classical data analysis, we are used to the data arrays, two-way tables where each case in a row is described by several variables that usually appear in columns. And this may be numerical or categorical, like here the number of passengers or the delay of flights, or the airline or the aircraft, which are categorical. But what if we are not interested in the flights, but we want to analyze the airlines? That is, from the flights data, we want to compare, possibly to cluster, to classify that the units of our interest are not individual flights for each of which we have data, but the airlines. Or in other problems of the type, if you have descriptors on purchases made on some supermarket chains or department stores, but you are not interested in analyzing the individual purchases, but rather the clients or groups of clients. In official statistics, this kind of problems appear quite frequently when you have data obtained on individual citizens, but you are interested in analyzing cities, regions, or some specific sociological groups. In those cases, data has to be aggregated. Look here at the example of flights. You have data on individual flights, but then if you are interested in the airlines, you have somehow to aggregate the data for each specific airline. Of course, this problem has been there for long. What people used to do is to comply with the data array model. The aggregation would be done by taking central statistics, by taking mean values, medians, if you want to be a bit more robust, or modes in the case of categories. But then there's a lot of information that's lost. So if we want to keep some more information, and in our case, if you want to keep and then take into account in the analysis the variability that was observed for each of the airlines, then you will aggregate keeping more than just a mean value. And here, for instance, for the variable delay upon arrival, we are gathering for each airline the empirical distribution of the delays. And here this would read that in 1/3 of the cases, the delay was below 10 minutes, 1/3 of the cases it was between 10 minutes and half an hour, and the remaining third, it was between half an hour and 1 hour. So an empirical distribution. For the case of number of passengers, you see that I recorded an interval, which can be seen as a special case of an empirical distribution where you consider just one interval defined by the mean and the max. In the case of categories, you can take a discrete distribution on the observed categories. And symbolic data analysis is interested in developing models and methods to analyze data as such. That is, to explicitly take into account the variability inherent to the data. For us now, the values of the variables are no longer the simple numbers, but they are finite sets, intervals, homogeneous distribution on an underlying set of subintervals or categories. That is, somehow we went from microdata to macro data, to use some terms that stem from official statistics analysis. And this approach has been introduced by Diday back in the end of the 80s of last century. In most common applications, in fact, such data that we call now symbolic data arise from the addition of microdata, as in the example that I have just shown. But it also happens that they are often reported as such when you have records for temperature, means and max, variation temperatures within a day or a week or a month, in financial assets daily means and max or open-close values, but also directly in descriptions of concepts like descriptions of diseases, of biological species, of technical specifications, where the values given are not constants. The variability is in fact expressed. Also sometimes appear quantile lists like for infant growth, plant measures, and the like. So the new variable types that add to the classical numerical single-valued and categorical single-valued variables now add new cases where you allow for multiple values. And then in the case of numerical data, you also have interval-valued variables where an interval of values is recorded, or distributional variables where histograms or quantile lists are recorded. And this is where we are focusing now. So let's now, given this introduction, let's concentrate on a specific problem. Bacteria the bacteria that we are addressing can be classified in gram-positive or gram-negative. And the distinction between them is that gram-positive bacteria do not feature an outer cell membrane that is found in the negative ones, in the gram-negative ones. So we have a data set of 23 species of bacteria, and we want to classify them according to the frequencies of each nucleotide in the genome. Let's see a bit into more detail. So we rely on data from the complete genome sequences of 11 gram-positive and 12 gram-negative bacteria, which were downloaded from a gene bank. Of course, you all know now that the genome is the collection of genetic information, where the gene is the basic unit recorded. And they are expressed as sequences of codons composed by sets of 3 nucleotides among adenine, cytosine, guanine, or thymine. So here are the 23 bacterial species, and you see that for each of which we have several hundreds or thousands of genes recorded. So for each species of bacteria, there's a lot of information which is of this type, like 1 gram-positive and 1 gram-negative. You see, for each of which you have more than 4,000 genes. So the data is like this. For each species, a large number of genes is available, is present. For each gene, the full gene sequences is given, which is a series of codons, so the 3 nucleotides, adenine, thymine, guanine, or cytosine. And what our biologist colleagues record and are interested and think that is related to the classification of bacteria into gram-positive or the gram-negative, it's the percentage of each of the nucleotides, the percentage of A's, T's, C's, and G's. So this is the data that we have. But remember, we are interested in classifying the species, not the genes. So for each species, there's a lot of information that has to be aggregated so that we have an aggregate description of each species that would allow then to proceed with classifications. So what we'll do is that for each species will be described by the distribution of the frequencies of each nucleotide, A, C, G, or T. So we have 4 variables, which are distributional variables, and the empirical distribution of the frequencies is recorded for each species. And this is the main study. But remember that the gene sequence is in fact a series of codons of 3 nucleotides. We also considered a more refined study where we consider the distribution of the frequencies of each nucleotide separately in the first, second, or third position. So taking not just the global frequency, but the frequency in each of the positions of the codons, and then compare the classification results based on this data. So now that we understand that to solve our problem, we have to take into account the distribution of some variable here, the frequencies of the nucleotides, we have to know how we will model this distributional data and how we can define a discriminant function to then classify the bacteria. So we proceed to the third point, where we address the modeling of distributional data, numerical distributional data in our case. So we need to see how we represent numerical distributional data, and this will be so-called histogram valued variables. Then we'll define how we make a linear combination of such distributional valued variables, and on the basis of which we present a discriminant method for the distributional data, and finally classification rules to assign observations to one of the 2 groups. Histogram valued variables mean that the observation of each unit, in our case it will be each bacterial species, it comes in the form of a histogram. Histogram, like we have learned in our first statistical course, a series of subintervals of non-overlapping sequentially consecutive subintervals, each of which assigned a weight, and the weights add up to 1. So just the standard histogram. And if we assume a uniform distribution, as is usually done within each subinterval, then the histogram may also be represented by means of the associated quantile function, which, because of the uniformity hypothesis, is just a piecewise linear function. And then you may ask yourselves at this point, why would she go from the histogram to a function, and why the quantile function, which is the inverse of the cumulative distributional function, and not the distributional function directly? Well, we take a function because, remember, we have to operate with them to define linear combinations in particular, and to define classification rules. And it's much easier to operate and to have an arithmetics for functions than for histograms. Everything is well defined and we know how to operate it. Then, remember, we are in a multivariate setup. We want to make linear combinations of the functions. So it's appropriate to use the quantile functions because they are all defined in the same domain, which is the unit interval between 0 and 1, which is not the case for the cumulative distribution functions. So we'll work with the quantile functions as a way to represent the empirical distribution. And here is an example for the first variable, distribution of the frequencies of nucleotide A in the Staphylococcus aureus species. Here is the observed histogram, as you can see, with 4 subintervals, which are defined by the quartiles. And here is the associated quantile function, a piecewise linear function. Here you have the graphical representation, the histogram, and the quantile function. And as you see, you look at this histogram and you are perhaps thinking, this is not how I remember a histogram. Usually the rectangles have different heights. Well, you can, when you aggregate the individual data, you can either fix the subintervals and then have random weights, or fix the weights, fixing some predefined set of quantiles, and then the lower and upper bounds of the subintervals will be random. And this is what we have done here. And the reason for this is, again, an operational one, because then the quantiles that you choose to define the subintervals of the histogram will be the limits of the different branches of the piecewise linear quantile functions. And it helps, of course, to have all functions defined with the same branches on the same subdomains. Okay. Now, we do need a distance, a measure of difference, of how to quantify the difference, the distance between two such distributions. With the real numbers is easy. You just take a difference or a square difference. But if you are distributions, how are they to be compared? Of course, there are many measures in the literature for distances between functions or between density functions, between distributions in general. We shall rely on the Mallows distance. Given two quantile functions that represent distributions, and distributions or intervals, but we shall take intervals as a special case, then the Mallows distance is defined as the square root of the integral over the unit interval of the square difference between the two quantile functions. If we do assume uniform distribution within the subintervals, then it's easy to see that this Mallows distance is just the squared Mallows distance is just the sum, the weighted sum of the Euclidean distance between the centers of the subintervals and the weighted distance between the half ranges of the subintervals. So very easy to operate with, in fact. And this is the result obtained by some Italian colleagues. Now, given that we have a distance, we have a means to obtain a central distribution, a barvcentric histogram, which will be just the distribution or the quantile function represented by a quantile function, the barvcentric quantile function that minimizes the sums of square Mallows distance to all of the observed ones. And this is, in fact, just a quantile function where centers and half ranges are the classical means of the centers and half ranges of all the given observations. Importantly, the Mallows distance and the barvcentric histogram or barvcentric distribution allow for the Huygens theorem that presents the decomposition of total dispersion around the barycenter in between groups and within groups dispersion. A decomposition that is the basis for many methods in multivariate data analysis, and particularly in discriminant data analysis. Now, we need to define a linear combination of quantile functions. Remember, we are looking for a method for linear discriminant analysis. So a linear combination of the quantile functions. And of course, the most straightforward way would be just to make a linear combination, a simple linear combination of the observed functions for the different variables. But this is not the way it should be done. And why not? Because the space of quantile function is not a linear space, it's just a semi-linear space. Quantile function is not just any type of functions, they are non-decreasing functions. They are the inverse of the cumulative distribution functions, so they are non-decreasing function. Therefore, if you multiply a quantile function by a negative coefficient, you obtain a decreasing function, which could never be a quantile function of any distribution. It's not a linear space. A way out would be to impose non-negativity constraints on the coefficients, but then you would be imposing a very particular kind of linear combinations where only direct linear relations between the outcome, the scores, and the observed variables would be allowed for. And this is also a restriction that nobody wants to impose on their models. With some ideas, a proposal has been presented to address the semi-linearity of the space of quantile functions, and this has been successfully applied to regression problems. What does this consist in? It consists in considering in the linear combination two terms by explicative variable. So for each explicative descriptor, for explicative variability descriptor, there are two terms in the linear combination. One that represents directly the quantile function of the observed data and of the observed histogram, and one which is the quantile function of the symmetric histogram. And with two terms per variable in the linear combination, we can now impose a non-negativity constraint on the coefficients and still not impose a direct relation. It may be assured that there is no multicollinearity problems because these functions, the quantile function representing histogram and the quantile function representing the symmetric histogram, are generally not collinear. Okay? Of course, this doubles the numbers of coefficients to be estimated. Sorry. So now we may proceed to discriminant analysis. We know how to define a barycenter, and we know how to define a linear combination of quantile functions. Here is with a parallel of what we are all used to, the classical model for linear discriminant analysis, and how it's set up when you have distributional data. So the linear discriminant function in the classical setup is just a simple linear combination of the observed real-valued variables. In our case, the discriminant score will also be defined as a linear combination in the way we have just defined of the quantile functions of the observed and the histograms and their corresponding symmetric histograms with non-negativity restrictions on the coefficients because of the semi-linearity of the space of quantile functions. Then, to obtain the coefficients in classical linear discriminant analysis, we rely on the decomposition of total dispersion around the mean in between and within matrices of sums of squares between groups and within groups. The same can be done because of the Huygens theorem that allows for the same decomposition. And therefore, the quadratic form gamma transpose T gamma that the quadratic form based on the total dispersion can be decomposed in the sum of two quadratic forms with the between and within matrices. The same applies now in our case. The same decomposition is valid. But T, B, and W are now 2P times 2P matrices. P is the number of descriptors, because remember that for each variable we have two terms in the linear combination. To obtain the coefficients gamma for the optimal discriminant linear combination, we maximize the ratio of the two quadratic forms between considering the between and the within sums of squares. In our case, we shall also maximize this ratio of quadratic forms, but now with non-negativity restrictions on the coefficients. And what, in the classical case, is just a straightforward optimization problem to solve, is now a hard optimization problem. In convex, it's easy to find a solution, but difficult to prove optimality. And here is where we really needed optimizers knowing what to do. To solve this optimization problem, we rely on conic optimization and rewriting the optimization problem in this way here. We're using the cone of completely positive matrices and relying on the work by Paula Brito, Manuel Bons, and Judith on copositivity and constrained fractional quadratic problems. And this has allowed to solve the problem. The final step is to have a rule for classification in the two groups, and for this we rely on a distance-based rule, on the Mallows distance. So an observation, that is in our case a species of bacteria in the application, will be assigned to the group for which the Mallows distance between its score and the score of the barycentric histogram is minimum. So distance-based classification. We have developed a simulation study to understand how this method behaves. And for this, we have considered histograms based on data simulated according to different distributions, uniform, normal, log normal to have some skew distribution, and also a mixture of distribution. We have considered different levels of separation between groups based on mean and standard deviation to be similar or different. Considered 3 descriptors, 2 groups, which should be balanced or unbalanced. In the learning sets, small cardinals in the or larger groups. For the test sets, even larger groups, again, balanced or non-balanced. And just summarizing the simulation studies, here are some graphics of the hit rates in the test set for the balanced and the non-balanced case. And we see, of course, when both the mean and the standard deviations are similar between groups, the problem is much more difficult. When at least one of them is different, the results are quite good. And some summary of the simulation results, similar for the 4 different distributions considered. In general, increasing the difference between means and standard deviations, of course, provides a better discrimination, as would be expected. In the learning sets, the mean of the hit rate is slightly higher for large samples. In general, the percentage of well-classified observations is influenced similarly by differences in the mean and in the standard deviation. In the skewed case of normal distribution, we saw that when the mean of the 2 groups is quite different, the increase in perturbation in the standard deviation is not really helping much more. And then back to our bacteria. So remember that in case 1, we wanted to classify the bacteria as gram-positive or gram-negative from the global distributions of the frequencies of the 4 nucleotides, the ACTG, whereas in case 2, we had 3 sub-studies where we considered the frequencies of the nucleotides, but just in the first, in the second, or else in the third positions of the codons. In each case, we have the 23 bacteria. It's more or less balanced groups. We have aggregated the data from the individual genes in histograms with 4 subclasses with a constant frequency of 25%, like you saw in the small example I showed before. The 23 species were considered to obtain the parameters, and then leave-one-out cross-validation was applied. To obtain the parameters of the linear discriminant function, Barron optimization method was applied. And here are the results. When the global frequencies are considered, we obtain a hit rate of 78% with leave-one-out. And there are 5 out of the 23 species of bacteria which were misclassified, and which, according to our biologist colleagues, are the most difficult ones to classify. When only the first, the second, or the third position in the codons are considered, the results are slightly worse, but we notice that it is the first position that better codes the information about the type of bacteria species. Here below is the expression of the linear discriminant function. The score is a quantile function. A quantile function that is a linear combination of observed quantile functions. For each variable, we have 2 terms. And we notice here, it's completely by chance, that you have a repetition of coefficients. But this need not be the case, of course. Also, do not be misled by the fact that you have minus signs. The coefficients must all be positive, but here the quantile function is written not as a function of t, but as 1 minus t, and therefore the minus sign appears. Okay, it's just a way of writing. So finally, drawing some conclusions and perspectives. So with this kind of approach, we went from the classical, the recorded microdata to macro or aggregated data. and considering distribution valued data where an empirical distribution is observed and is recorded for each unit, which takes a special case when we have interval valued data. And this allows to take variability into account in the representation and analysis. In our applications, we used histogram data, and for this kind of data, the proposed methods are based on the Mallows distance between quantile functions. I did not stress this, but in case you have degenerate distributions when the values are indeed constant, then the Mallows distance is nothing more than the Euclidean distance, the standard. So we go back to standard methods and standard measures as a special case. We have proposed a linear discriminant method for numerical distributional data, relying on linear combinations of quantile functions of the observed histograms. The performance was evaluated by means of a simulation study with different setups, and then applied to the classification of bacteria into a priori groups. What is on the table? For the bacteria classification problem, we already do have a much larger data set, much more than just the 23 species that is being processed. We have to study the effect of degradation granularity. That is, we have chosen to aggregate the microdata from the thousands of genes into 2 sub-intervals for each histogram, but we could have considered just one interval or a different number of sub-intervals, 4 or 5. And so how this impacts the classification results is something that should be addressed. Of course, the whole methodology has to be extended to more than 2 class problems by considering either 1 versus 1 or 1 versus all strategies. And then the next step is to go from histograms to estimation of densities and define the whole methodology for densities. And this is the PhD of Rui Nunes, a student that is starting now to work with me and Sonny Dias. Because, of course, this is an open field, there are new problems which present new challenges as distributions are not real numbers. Standard properties may not be taken for granted, and many things have to be readdressed. But already in the 80s of last century, Schweizer was saying that distributions are the numbers of the future. And this is, of course, the case in the era of big data. Before I finish, I'd like to take this opportunity to draw your attention to the conference that we are organizing in Porto next summer. This is the 17th conference of the International Federation of Classification Societies under the motto of classification and data science in the digital age. And of course, you are all invited to come, to submit and to come. I should say that most of the works I've seen presented in this webinar series fit very well to the conference. In particular, there's a special track on optimization in classification and clustering. And among the publications, we'll have pre-conference proceedings with Springer, but post-conference special issues and highlighting the special issue of the Euro Journal of Computational Optimization on modern optimization approaches to classification. And you'll find us on the conference webpage. I hope to be able to welcome you all in Porto next summer. Thank you very much for your attention. I'll be more than happy to answer some questions should you have some. Thank you.
Thank you, Paula, very much for your interesting presentation, and really good to see also the conference and the invitation to the audience here. Are there any questions for Paula? And you know that if you raise your hand, we will give you the right to unmute.
I have noticed that Paula Amaral, who is co-author of this work and really supported us in the most optimization problems, is also online. So if there are questions specific to the optimization method applied, she perhaps can also intervene.
I have a question, but you have to forgive me because it's not my expertise, but when you show these histograms, is it the level of granularity of the representation of the data? Is it given, or is it something that you can
it's a
manipulate?
user choice. It's a user choice. It's not given. I mean, unless someone imposes, but in principle not. So this, and it will impact the results. So this is, in this particular application, it has to be studied. But we know that considering a histogram with more classes or just an interval will make a difference. Of course, you cannot have many subclasses if you have not many observations. In this case, this would not be a problem because you have thousands of genes for each species. So we really could consider more than 4 subclasses, say 5 or even 10, and this still there's a lot of observation that histogram makes sense. And to understand how this impacts the results is of course of interest.
Thank you.
Yeah, you're welcome.
Are there any questions from the audience? Yeah, I think it was all clear.
Thank you. Anyway, people, I mean, I would be happy to engage in some discussion if people have questions later on after seeing the slides or the video, and can write, of course.
Yeah, exactly. You know that lots of people later on go to the YouTube channel and watch it. Yeah. So thank you very much, Paula, for this very nice presentation, and thank you for the audience for coming back, and see you next week with our next speaker. Thank you.
Thank you very much for this nice invitation again. It has been a great pleasure.
Thank you so much.
Thank you.
Thank you, Itzia.